Cedar Point is the roller coaster capital of the world. However, has anyone thought about the physics behind the rides? Besides the roller coaster technicians and manufacturer, of course. One of the most popular rides at Cedar Point is the hanging roller coaster, the Raptor, and it also has some pretty cool physics behind it as well. The Raptor was built in 1994 by the manufacturer Bolliger and Malabard, who is responsible for building the Vortex, Dragon Con, and Batman the Ride. When the ride was opened in '94, it broke a multitude of records for being the tallest, fastest, and longest inverted roller coaster. It was also the first inverted roller coaster to do a cobra roll. The Raptor has a maximum height of 137 feet, a drop of 119 feet, and it tops out at a speed of 57 miles per hour. The Raptor is a decently long ride, with a ride time of 2 minutes and 16 seconds due to its length of track, which is 3,790 feet long. The ride has 6 inversions, a vertical loop, a heartline spin, a dual twist cobra roll, and a pair of twisting corkscrews. These are the major structural components of the ride. The Raptor cost about $12 million to make, but it surely made a return in profits due to the spike of popularity in the ride. So let's dive into the physics of this ride. Firstly, the ride is inverted, so that means that the train runs under the track and the seats are attached to a wheel-like carriage. A 9,000-pound chain pulls the roller coaster up the steep incline leading to the first drop. All of Newton's 3 laws play into effect of the inner workings of the roller coaster, as nothing powers the ride. Newton's first law, inertia, allows a roller coaster to completely go around and complete the track from its own inertia. Newton's second law allows proportional acceleration, and Newton's third law allows an action-reaction force keeping riders in their restraints. The law of conservation of energy also allows the Raptor to function, as it switches between gravitational potential energy and kinetic energy to continually go around the track. However, energy is lost through mechanical, heat, and sound energy. We can judge roughly the gravitational potential energy and kinetic energy of the ride through estimations. The weight of the cart is around 1,500 kilograms, and the height of the drop is about 41.75 meters. We can use the equation potential energy is equal to mass times gravity times height to solve for gravitational potential energy. If we were to plug in the figures above, we can figure out that the potential energy would be 613,725 joules. Kinetic energy can also be solved through the equation 1/2 mass times velocity times 2. Kinetic energy, if we plug in those figures for kinetic energy, we get 15,165 joules.